Okay, so question 50. For each of the following, indicate which is the most stable. So there are 4 questions here. Definitely suggest you do them all. These 2 are the only ones I'm going to play around with, sub-question B and D, and I'll let you do the other 2 on your own. So what we're going to have here is, for sub-question B, we have 2 carbocations. And so the first thing you should think of is carbocation stability and what influences carbocation stability. You should remember from your book and lecture that in terms of stability, tertiary carbocations are more stable than secondary carbocations, which are more stable than primary, which are going to be more stable than methyl. Oops, get rid of that. Okay, so tertiary to secondary to primary to methyl, and that's the order of stability. Tertiary being the most, and methyl being the least stable. Okay, so here what we have, let's try to first categorize both of these by tertiary, secondary, primary, and methyl. So here we have 2 R groups, a methyl here and a methyl here, attached to the carbocation. So this is going to be a secondary carbocation. And here we have a methyl group and a CH2 group. So overall, they are both secondary. So we have a secondary here and a secondary here. It doesn't matter that this is a CH3 versus this is a CH2. The fact is that you still have 2 groups attached that are not hydrogen. So we're going to have a secondary and a secondary. Okay, so obviously this isn't the main issue affecting stability. One of them will definitely be more stable than the other, but we have to go a little bit deeper than just talking about tertiary, secondary, primary. So for this example, the only big difference here is the chlorine. So we have a chlorine, and the chlorine or any halogen can affect stability in one of 2 ways. The first way is via induction, and the second way is via resonance. So in this case, this chlorine cannot partake in any kind of resonance at all. So you could prove this to yourself by trying to do the following. So if we did this, and we tried to have the chlorine donate electron density by resonance, what we would get would be the following compound. So we would end up getting this chlorine with 2 lone pairs on it, and overall this guy is going to be positive. Okay, so you can prove that to yourself by doing a formal charge calculation, and then after that we would have to calculate where a negative is coming in. So it looks like if the chlorine's positive, the carbon's probably going to be negative. So let's think about that for a second. There's something wrong with this. So if you don't see why there's something wrong with this, pause the video and think about it. Okay, so let's think about the atoms that are attached to this carbon. So what we really have here are 2 hydrogens, hydrogen here and a hydrogen here. So if we make a new bond between the chlorine and the carbon, we haven't actually affected those 2 hydrogen-carbon bonds. So they're still there. So the issue here is that we now have a Texas carbon. We have a carbon with a valence of 5. So 1, 2, 3, 4, 5 covalent bonds to carbon, which is impossible. So we're breaking the octet rule, which is impossible to do for carbon. So this guy's right out. So we can't actually do this. So this is impossible. So we have to figure out another way that the chlorine could potentially be affecting the carbocation. Okay. So in this case, it's actually a bit more subtle. The chlorine is not doing any kind of resonance contribution, but it is actually doing an electronegative inductive contribution. So there is going to be a little bit of an electronegative pull on the electrons over this way. So we're going to end up having a partial positive on this carbon, partial negative on this carbon. And so you can think of this pull not only affecting this carbon, but to a certain degree, this carbon as well. So we've already said that if you have a deficit or an excess, it's going to be bad for your molecule in terms of stability. So I'll say it over and over and over again that nature hates an excess and nature hates a deficit. So right now, we already have this carbon in a hole. It already has a deficit. So anything that increases that deficit is going to destabilize the molecule. So as this chlorine is pulling electron density away from the carbon, we are increasing the electron deficiency of this carbon, and so we're increasing instability. Okay, so overall, this guy is not so much a secondary as maybe more primary-ish. So that's one way you can think about it. Even though it's technically a secondary carbocation, it is becoming destabilized almost to the point of becoming a primary carbon or primary carbocation. Okay, so of the two, this carbocation is going to be more stable. So going on to the second question, or second sub-question, sub-question D, we have two alkenes, alkene here and an alkene here. And the way that we categorize stability of alkenes in class is very simple. If you have the same number of attachment points onto the alkene, the E is going to be more stable than the Z. However, in this case, we have a differing number of attachment points. So for this alkene, we have 1, 2 attachment points. And for this alkene, we have 1, 2, 3 attachment points. So 2 attachment points here, 3 attachment points here. So we had already said in class that the more R groups that you have attached to your alkene, the more stable it is. So this alkene is going to be more stable. Okay? And this alkene is going to be less stable. And it's actually as simple as that. Okay? Next question.